Hello and welcome to the I Heart Pluto Festival. I'm Dr. Jennifer Hanley, a planetary scientist studying liquids across the solar system at Lowell Observatory. This year we celebrate the 4th annual I Heart Pluto Festival, centered each year around February 18th, the date that Lowell Observatory's Clyde Tombaugh discovered Pluto in 1930. The festival is a community-wide event that includes science talks, family activities, a keynote program called Night of Discovery, which took place on the 18th and featured NASA astronaut Nicole Stott, a Pluto pub crawl, Pluto-themed food and drinks around Flagstaff, and more. We'd like to thank the following sponsors for supporting the festival: Unisource, North Country Healthcare, APS, Arizona Central Credit Union, Dark Sky Brewing, Creative Flagstaff, and the City BBB funds. And a special thank you to Unisource for sponsoring this virtual program. Tonight's program will be New Horizons, NASA's mission to Pluto and the Kuiper Belt. The talk will be given by Alice Bowman, New Horizons Mission Operations Manager, or MOM. Alice is a member of the Principal Professional Staff at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. She supervises approximately 50 staff members who operate deep space and Earth-orbiting spacecraft, including NASA's TIMID, Stereo, New Horizons, Parker Solar Probe, and recently, DART. Alice's experience also includes national defense space operations, systems engineering, program management, space systems, and space instrument development. Alice has a degree in chemistry and physics from the University of Virginia and has more than 30 years of experience in space operations. During this program, viewers are welcome to send in questions via the YouTube chat, and they will be answered as time permits. With that, I will turn it over to Alice.
Thank you so much, Jennifer. Okay, I'm going to be sharing my screen. Okay, just checking the settings here so that I don't get surprised. Okay, thank you so much for inviting me to this, to speak at your festival. It's quite an honor. I had the opportunity to visit Lowell Observatory, and it's quite a fascinating place. So thank you. So I'm going to be talking about the New Horizons mission. We flew by Pluto in July of 2015, and then on to a smaller Kuiper Belt object recently named Arrokoth in 2019. Just a quick recap of the solar system. Here we have the sun, and I'm showing that 1 astronomical unit, or AU, is the average distance between the sun and the Earth. So that is this right here. And then look over here where Pluto is. When we encountered it, it was about 32 AU, or 32 times the distance from the Earth to the sun. And then Arrokoth, this other Kuiper Belt object way out here, we encountered it when it was 43 AU from Earth. Important thing to keep in mind is that it takes a photon about 8 minutes to travel from the sun to the Earth. And the reason why I want to point that out is because when we talk to the spacecraft, we communicate with the spacecraft, we send information at about the speed of light. And so at these distances, you can understand how long it takes a signal to go from Earth to our spacecraft. And from when the spacecraft sends data back to the Earth, it takes that long to get back to Earth. And I have some slides later on that will try to explain that. So this is Pluto before New Horizons visited it. And if you ask a scientist, they're going to say, while this planet is going to be extremely interesting because there's a lot of contrast in this picture, but perhaps if you ask the average person, they might say, well, I'm not so sure it would be very interesting. But this was taken with the Hubble Space Telescope, which at the time was our most powerful telescope that we had. So New Horizons is the first spacecraft to visit the Kuiper Belt. We launched January 19th, 2006, and we followed this red path, and we flew by the Jupiter system in February of 2007, so just 13 months after launch. We used Jupiter as a gravity assist, and it shortened our transit time to Pluto by 3 years. And even at that, it took us until 2019, or 9.5 years from launch, to get to the Pluto system. And then 1 billion miles beyond Pluto, there's this very small object called Arrokoth that we encountered on January 1st, 2019. And this region here, this donut-shaped region, is the Kuiper belt. So the spacecraft is pretty small when it comes to spacecraft. It's about the size of a baby grand piano. It weighs just over 1,000 pounds, and we have 7 instruments or payloads on board the spacecraft that take scientific measurements. So we have particle instruments, SWAP and Pepsi and SDC down here. And then we have UV spectrometer, the radio science experiment, which is we used with the RF system on the spacecraft. We have LORI, which is our high resolution camera, and we use it for satellite searches, navigation. It's a black and white camera. And we have Ralph here that actually has 2 instruments embedded in it. It's a visible camera and also IR spectrometer. I think I got all of those. All right. And it's powered by a nuclear power source. So if you're familiar with nuclear power, you launch with a certain amount of power, and then as time goes on, that power decreases. It's just a natural decay of the power source. So as I said before, there are many challenges to this mission, and it's one reason why it took us so long to send a spacecraft to Pluto. The system is very, very far away from Earth, so 32 times the distance between the sun and the Earth. And as I showed earlier, it took us 9.5 years to reach Pluto, and that was using Jupiter as a gravity assist. And we need a spacecraft that can take care of itself, because with those large distances, it's going to take a lot of time for the operations team on Earth to take care of any problem that we see on the spacecraft. I'll talk a little bit about that later on. Power, we had to use a nuclear power source because if we were to use solar panels, they would have to be extremely large, size of a football field. And like all first reconnaissance missions that NASA does, this is a flyby mission. You only get one chance to get it right. You can't turn around and have another go at it. So I'm the mission operations manager, and I lead the team, the mission operations team that keeps the spacecraft healthy. We work with the scientists and the engineers to develop commands to perform their objectives. So the engineers might want to do calibrations and checkouts, and the scientists might want to do calibrations on different stars each year. They want to take measurements. And so we take all that information and we build the commands that go to the spacecraft. We also develop that schedule of events, when it's best to do these things, how we're going to schedule the communication time with the spacecraft, when we're going to get the data back. And then we set up the Deep Space Network, which is the communication system we use on this spacecraft. And we have it match what is being sent from the spacecraft so that we can get that data to Earth. And importantly, when there's something wrong with the spacecraft, we're the team that responds and fixes any issue on the spacecraft. Of course, we bring in the whole team to help us. It's definitely a team effort. So this is a short little video of the Deep Space Network, or DSN. There are 3 complexes around the world, about 120 degrees apart. There's one at Madrid, Spain, Goldstone, California, and Canberra, Australia. And so you can see as your spacecraft moves away from Earth and the Earth rotates, you can use one of these complexes to be in contact with your spacecraft. So just a quick example of how to illustrate the distance, the vast distances that we're talking about when you send a spacecraft out to the edge of our solar system. And again, this is just, it's not to scale. And I'm using the example when the spacecraft is at Pluto. So when the spacecraft's about 32 AU from Earth. So here at the bottom, we have the ground antenna on Earth. And then we have the spacecraft here up in the sky. Well, out in space, sorry. We load commands to the onboard memory on the spacecraft in about 2-week period pieces. And so there is an onboard clock, and each of the commands is tagged with a certain time. And as that onboard clock ticks down, when it matches the command with that same time, then the command executes out of memory. So what I'm showing here is that spacecraft is programmed to start sending telemetry so that it can be intercepted or captured by the antenna on the ground. So here we are at time 0 sending telemetry. That antenna can be supporting a different mission. And then finally, that telemetry is about halfway down. Pluto at 32 AU is 2 hours and 12 minutes. It's halfway to Earth. The spacecraft is continuing to move across the sky. And then finally, that telemetry is received at the ground antenna. But look how far that spacecraft has moved across the sky as viewed from Earth. So you can see it moved quite a bit. And likewise, if you want to send information to your spacecraft that's really, really far away, you point your ground antenna to where the spacecraft's going to be, and we call this a one-way light time later. So it's the time that it will take information traveling at the speed of light to get to the point in space where that spacecraft is going to be. So here we go. The sending the information is about halfway there. Spacecraft's making its way across the sky, and then finally it's captured a one-way light time later, 4 hours and 25 minutes in this example. Again, using Pluto, the spacecraft at Pluto. So when we encountered Pluto, we carefully planned out the set of observations that were going to take place. And we chose a 9-day period. There's many reasons for that, but this 9-day period was chosen so that we would have time to recover a spacecraft should we have an issue. And it was also encompass the early part of the observation campaign, and then extended 2 days beyond the closest approach. So the closest approach date was July 14th, 2015. Our first opportunity to put this set of commands on board the spacecraft was on July 4th. You can imagine that with all these observations, the amount of commands required to take this once-in-a-lifetime set of activities was huge. So we had to wait until there was enough memory cleared on board the spacecraft before we could actually load it to the spacecraft. And besides loading it to RAM, we also had to load it to discrete memory. So we had to write it to flash memory. And this was because if we had a fault condition, we wanted to be able to recall those commands out of flash memory and put them back on the spacecraft without having to upload them again to the spacecraft from Earth. So at this time, the round trip light time, 8 hours, 49 minutes, one-way light time, again, 4 hours and 24 minutes. So on July 4th, we started uplinking this set of commands at about 4 in the morning. And a one-way light time later, a round trip light time later, we watched those commands being received by the spacecraft. Now, remember, we're watching telemetry that is basically 4.5 hours old. So we're looking to what the spacecraft was doing in the past. And at about halfway through loading those commands to the spacecraft, we lost all communication with the spacecraft. And that was a terrible feeling. I think our scientists were thinking that the spacecraft encountered some small piece of dust that caused some catastrophic damage because we were traveling very fast. On the engineering side, we were wondering what the heck did we do to cause something like this? And we had about 5 people in the Mission Operations Center, started troubleshooting. And we determined that what happened was that we'd asked the spacecraft to do too many things at one time. And it actually decided that there was something wrong with the computer because it wasn't responding and it went into a safe mode. This was on July 4th. So on July 5th, we sent our first set of commands to recover the spacecraft. And over the next few days, on July 7th, we got the final confirmation that the spacecraft was ready to conduct the flyby of the Pluto system. So we had about 4 hours to spare, but it's something that even though we had planned this out to the very smallest detail, I guess that just shows that, you can't, there's always something that you haven't accounted for. So July 7th, our 9-day flyby sequence started, and we got some awesome data. And I'm going to fast forward here to the right before closest approach. So here we are, closest approach for us, we call it the aim point, 11 hours, 49 minutes, 57 seconds. And this is in UT time. Down here, we had our last track with the Deep Space Network. I think it was a Madrid antenna, the 70 meter out of Madrid. And we checked to make sure that the spacecraft had everything that it needed to do the flyby, and that everything looked good on the spacecraft. And then because our spacecraft, you can't take data and be in communication with Earth at the same time. So basically, the plan was to fly through this whole period without a communication to Earth, because this is where you get the best science. And so we did not want to interrupt that. So we had our last contact here, ensuring everything was okay with the spacecraft. And I'm going to show you what the spacecraft was doing in this 22 hours. It's shrunk down to about 20 seconds, so you don't have to worry about having to watch something for such a long time. And then at the very end, I'm going to show you what happened when we took 15 minutes out of the observation sequence and had the spacecraft turn, point to Earth, and send us a burst of data so that we could evaluate how things were going on. So let's see. So here's our spacecraft. Up here, you can see the instrument that is being used to observe, and you can see the distance to Pluto, the speed, etc. So here we go. We're almost at closest approach, and there we go. And we're looking back. And so this is just redoing the simulation so you can see it. So there's no gimbal parts on the spacecraft, so that's why the whole spacecraft moves when you take an observation, and that's because gimbal parts on the spacecraft, or moving parts in the spacecraft, are the first things that might go wrong. And of course, with a long duration mission, you want to take you don't want to take any chances that you don't have to with designing a spacecraft that you want to design it so it's robust. Oops, I'm not sure. Okay, so here we are. We flew through this part here, and we're going extremely fast, 31,000 miles per hour. And now we're coming up on this track or communication period with the spacecraft. This is our chance to see if the spacecraft survived. And if it didn't survive, we aren't going to see it here. We're not going to get a signal from the spacecraft. We're also going to be able to tell, we won't get any images back, but we'll be able to tell if the amount of expected data was recorded on the spacecraft. So we kind of have like a measurement of what we expect. And so this next is a little video that shows that moment in the Mission Operations Center when we are trying to confirm if we had a successful flyby. The Operations Center is not very big, but pretty much the Mission Operations Center is very full. Part of that reason is so that if we have to deal with any problems, we have the people there on hand. And we have our managers in the back room with the agreement that we will assess the status of the spacecraft before they are invited in. So here we go. Oops, sorry.
And lock on symbols.
So that's the first step to getting data.
Okay, copy that. We're in lock with telemetry with the spacecraft.
See a lot of green numbers in that book, too.
Green is good.
Yeah.
You gotta get that, man.
Okay. PI, Mom on Pluto 1. We have a healthy spacecraft. We've recorded data of the Pluto system, and we're outbound for Pluto.
Yeah. That's it.
Okay, you can see that was a quite exciting night for us, and we're a bunch of engineers, so we weren't used to having all those cameras around us, but it was quite a special night. Many of us worked on that, get the spacecraft to Pluto for tens of years, and our PI, who you saw at the end, has spent pretty much most of his career working to get a mission to Pluto. So we were all pretty astounded and happy and overjoyed that everything worked. So how did we do? So again, this was the aim point. Here's the aim point. And if you would memorize what that number was on the first screen that I showed you, you can tell that we didn't quite hit it spot on, but we were within the error box. We came, and this is from 3 billion miles from Earth. So here we are, sort of a hole in one. And we hit that aim point 88 seconds early and 26 miles off. So I would say that's pretty good from 3 billion miles from Earth. But I always like to tell people that if we hadn't had that little hiccup on July 4th, we would have had a little bit more nerve in trying to tweak that a little bit so we get closer. But that being said, this picture of Hubble, this is what the spacecraft saw. Quite amazing. This is a composite picture of the Ralph images and the Lori images. And the next video that I have is sort of a recap from launch of the space in 2006, the flyby of Jupiter, getting a boost, a gravity assist from Jupiter, and then the encounter with Pluto and some of the highlights of the discoveries, not all of them, but the highlights, and then the second part of our mission extension 1, which carried us to a very small Kuiper object called Arrokoth. So I'm going to play that right now. can see we're pretty proud of this little spacecraft and the things that we have accomplished. Okay, so our next part of our mission, extended mission, the Kuiper Belt Extended Mission 1, carries us to a very small Kuiper Belt object. Pluto is the largest Kuiper Belt object so far discovered. And this other object that we're going to is very small. It's just a few miles in diameter. And it has been named Arrokoth. And this was the name it got about a year after we encountered it. So on discovery of this object, it is called formally 2014 MU69. And then as we were preparing for the encounter, we gave it a nickname called Ultima Thule. So those three acronyms are the same for this object. And besides going for another flyby, we also were tasked with imaging other Kuiper Belt objects. And here are some of the names of the few that we have imaged. So you can see Korar and Maya's in here. And down here on the side, I'm showing the telescopes that we used on the side here. It's quite interesting. We would use the Subaru telescope out in Hawaii and do a search in the area of the sky where the spacecraft was, identify Kuiper Belt objects that might be candidates for a flyby, and then we use the Hubble Space Telescope to refine those orbits. And once we had that orbital data, we could turn around and put it into our command sets on the spacecraft and then do the imaging. And so that took about 9 months for this whole cycle, which I think is incredibly fast for discovering an object and then imaging it with a spacecraft. So just as in comparison, whereas Pluto was 3 billion miles from Earth, Arrokoth is 4 billion. And today the spacecraft is at 5.2 billion miles from Earth. Pluto, our flyby distance was about 7,800 miles. And then when they told us they wanted to fly by Arrokoth at 2,200 miles, I was like, oh my goodness, we don't know much about this object. And yet you want us to fly so close to it. And our light time delay, that much longer, about an hour and a half longer at 6 hours and 8 minutes. And then we're decreasing in power. So we're at 190 watts at Arrokoth, which means that we have to do a lot of power switching during the encounter to make sure that we don't oversubscribe the power. And we've only discovered this object 5 years before we actually fly by. So it's quite a challenging mission. So one of the things that our scientists can do to give us more information on the engineering side is to do these occultations. And there were 3 opportunities that they calculated where they could observe Arrokoth from Earth. One was and this was observed before we had to lock down the set of commands and start testing that set of commands. So there were probably more after this, but these 3 observations were the only ones that fit that timeline. So in June of 2017, this was actually in 2 places, in South Africa and Argentina, and sent out scientists with telescopes, and we saw no detection. So they went back and refined their calculations, get ready for the next observing period, which is July 10th in 2017. This happened to be off the coast of New Zealand, so that was, you can't set up a bunch of telescopes on land. So there is a NASA plane called Sophia. It has a 100-inch telescope on it. So they boarded the plane, told the pilots where they wanted to be at a specific time, opened the telescope door, took measurements. Of course, there were other instrumentation as well. But with only 1 telescope, it's hard to say. You don't have any corroborating information from other sources that what you saw was actually something detection. So last opportunity, July 17th, and this was off the coast of Argentina. And I'm going to show you a little video. Once I show you how they lined this up, this was the last opportunity to get information that would fit into our command sets. Where these lines are that have the little blue bubbles on them, this is where the telescopes were set up. And you can faintly see this red line, and this was predicted to be the center line, or the best place where we could get the most occultation with it. So just to recap, occultation is like an eclipse. So with an eclipse, you have let's just say it's lunar, so you have the moon coming across the sun, and wherever you are on Earth will depend on how much of a shadow you see. So a full eclipse or a partial. Same thing with the occultations, wherever you are on Earth. And when the occulting, the star is occulted by Arrokoth, depending on where you are, you'll see a full occultation or a partial. And so they wanted to make sure that if the calculations were off just a little, that they had all these distances covered, just to make sure. So the next is a video, and it's the scientists down in Argentina. It's winter time. There is a lot of wind, so in some places it might be hard to hear. They partnered with the local community and the local universities to bring in scientists for help, and of course the townspeople. So here we go.
Tonight is the big event. There should be a star that blinks out, but who knows if it's actually going to happen.
So this third occultation feels really important because if we don't catch the object this time, we'll have a lot less information going into the encounter.
I want to just say thanks to everyone for the past few days of work, and to some of you for the past few months of work. Let's go get the data tonight.
Minute, and I will tell you if I see the star disappear. Oh, I saw it.
No way.
I saw it. I'm pretty sure I saw it.
Holy cow.
I actually saw it.
Holy cow.
No, I really did see it.
That's it. We got it.
We as a team succeeded in getting not one, not two, but 5 different occultations. So we saw the star go out and come back as MU69 passed in front of the occultation star at 5 different locations.
All right, I don't care what the weather is today. That's a great feeling. Here it is Tuesday. It's rainy, windy, cloudy, really nasty stuff for astronomy. And it doesn't matter. It's great. It can do whatever it wants as long as I can get out on my airplane back to Buenos Aires tonight. It could snow 10 feet tomorrow for all I care. But we got what we came for.
So, quite exciting. They got what they came for, and you heard Khan say they got observed 5 occultations. Excellent. So here is these lines represent the view of the occultation star, meaning that the telescope saw the star this whole period. If it had, if Arrokoth had occulted it, you would see a break in this line. So on June 3rd, they did not see any indication of Arrokoth. And then here we are with the July 10th observation from Sophia. Again, just one telescope, and so they saw a little break there, but with only one instrument or telescope, it's really hard to say exactly what you're seeing. And then here we are. This is the telescope or the occultation that they observed in Argentina. And I just think this is astounding. 4 billion miles from Earth, and you're looking at an object that is less than 5 miles in diameter, so maybe 2. And here, look, it traces out this pattern, and you can actually see an object 4 billion miles from Earth. And even if you were manning a telescope that did not see the occultation, you're providing excellent data to figure out what this thing is. I just think that's pretty cool. So some of the shapes that might come to mind when you look at these observations, because we're looking at a snapshot in time. So we know that the object, or most objects, have a rotation period. So you have to figure out what period of the rotation are you actually observing. So we had artists on our team, and they came up with these different ideas of what this object might look like. Just to give you a quick snapshot of what was going on, we had these placeholders in our timeline on board the spacecraft where we could correct our trajectory if the optical navigation told us that we weren't quite on path. We had periods where we could make a decision on the flyby distance. If we saw something in our path that we thought was going to be a danger to the spacecraft, we could actually move farther away from the object. And then you can see we actually went into solar conjunction very shortly afterwards. And then close up on the timeline, we did have the opportunity where we could adjust when the observations were taking place on the spacecraft, so we could apply a delta time, either plus or minus, so that we could shift this a little bit if we needed to. And then so here we are, fast forward to about 48 hours before closest approach. And these are the images that were coming down from the spacecraft. So the raw image, and then the sharpened image, which is a process image. So you still aren't seeing too much. We're about 2 million miles from the object. And here we are. Oops. Hold on. There we go. Just a day before. So you can see it's taking shape. Here we are. We're just 24 hours before closest approach. And yet we don't see a lot of definition. And remember, we've got the LORRI instrument, which is what this is taken with, is it got about an 8.5 diameter field of view. And at a 2,200 mile distance, we could be really, if our navigation wasn't spot on, we could be looking at below, the object could pass above the telescope, we could clip it, or we could have it right in the center. And this picture is actually telling us that we are centered here. And then on January 1st, 2019, this is what we saw perfectly, well, almost perfectly in the center. 21 miles in the long direction, and I think it was like 9 miles maybe in the other one, but I think the next one will show. And then this is the processed image where we get a lot of distinguishable characteristics of this object. So you can see that it is a contact binary. But the interesting thing here is that there's no fissures. So it shows us that there was a gentle coalescing of these two objects, and they don't appear much difference in color between them. So we think that it wasn't combining by an impact from something coming from outside of this orbital place where these objects are, but a gentle joining. And so, you know, when you look at that picture, you think, well, it kind of looks like a snowman or BB-8, but we turned back and looked at the object. We turned the spacecraft back, looked at the object sunlit, and we saw this image. And our scientists are saying, wait, that is not round. That looks a little bit more flat than we expected. And so this is what, you know, first we thought they were balls, so the balls, round things together. And now with this interesting information that came back afterwards, we can see that they aren't round. It's kind of some people were calling it a walnut and a pancake. So how did we do? So here we are. So this is where, so we were thinking that we saw this period of rotation when we took the observations in Argentina. And then on Sophia, we think we're seeing the back end of the object sort of stuck in. So quite good. So you can think of New Horizons as looking back in time to where our solar system was in its formation and how things came together. And, you know, so we're really discovering the primordial building blocks of the planets. And so where is New Horizons going next? Everybody knows about the Voyagers and the Pioneers, so that's why they're on this chart. So here's Voyager 1, Voyager 2, and then New Horizons is here, is in the direction of Voyager 2, but not tipped quite as much down in the ecliptic. And right now the spacecraft is at about 54 AU. We're in our extended mission 2, and we have a number of observations that were planned. We are still looking for a third target to fly by. We haven't had much luck finding one, but we're hoping that JWST can help us figure out if there's one for us to observe. And these are, you know, I have the honor of speaking to you tonight, but this mission, it takes everybody doing their part to make it a success. And these were just a few pictures of the people, of the teams that are involved. And of course, we have a rather famous astrophysicist on our team. And here he is in the Mission Operations Center on December 31st, teaching me how to take a selfie. So I'm sure you know who he is, but if you don't, I'll tell you when the question period. And there are quite a number of books that have been written about New Horizons, so I just put a few here. The one called Little Spacecraft That Could, that's obviously for younger children. Mission to Pluto is probably middle school age. Chasing New Horizons is quite an interesting read of how the program came to fruition, all the little fits and turns it took. And then this large book here is a compilation of some of the papers that have been written and discoveries of the Pluto system. And I think that is it. I am more than happy to take any questions. So thank you very much.
Wow, thank you, Alice. That was such a great an interesting presentation. It's really nice to hear some of the more operations specific kind of challenges and how everything came together for New Horizons. I really appreciate that. So we have a few questions from the audience. We'll start back at the beginning. Can there be any way to use New Horizons as a form of wide-angle telescope?
If we had a lot of propellant, we certainly could do that, but we have a very limited amount of propellant, and we have to take the whole spacecraft to point the instrument to whatever object. So it's not a real efficient use of the spacecraft, and we would run out of propellant pretty quickly. We have about 9 kilograms left.
And does the spacecraft need 24/7 monitoring?
No, it does not. Spacecraft has a very robust autonomy system on board, which is the system that is monitoring it for any kind of faults, and will take action to keep the spacecraft safe should anything happen. So we generally, we monitor the spacecraft maybe 5 or 6 times a week for 6 or so hours each time. The spacecraft right now is in hibernation, and we monitor it once a week for about an hour and a half. So it's perfectly happy doing its thing without us.
And have any of the onboard systems experienced degradation due to being in space, radiation, etc.?
That's a good question. As far as we can tell, and we do calibration yearly or close to yearly, we have not seen any degradation, but we're on the lookout for it, because you would think after, 16 years in flight, you would start to see something, but no, not that I know of. We haven't seen any degradation. We are losing power like we expected.
And you might not know the answer to this, and that's okay, but what motivated the PI to spend his entire career on this?
So everybody loves a challenge, right? I don't want to speak for Alan, but I can only surmise that, this is the last planet that has not been visited. The last one before Pluto was Neptune in 1989. With the Voyager spacecraft. And who doesn't like a challenge,
Yes.
That's my guess.
So for anyone out there, there was an interview with Alan Stern yesterday, and you can find that on Lowell's YouTube page. And I think he talks a little bit about that. Yes, we have a few more questions here, and please continue to put more questions in the chat, and we'll get to them if we can. The next one is, have there been any aha moments in using the existing systems for new discoveries?
Yes, I am sure there have been, especially on the science side, but since I'm on the engineering side, we continue to find out things about the spacecraft. The spacecraft's at a point sits so far out from Earth that the zodiacal light has decreased, and so it's a good platform for observing sort of, I guess, more pristine type environment of objects that are really far away, because you don't have to, I'm sure you probably have to account for some of the zodiacal light, but not as much. It's not as much corrupted. We have been experimenting with parallax. So we have been, because if you think about, if you use Earth-based telescopes and the spacecraft, and you take simultaneous observations after correcting from light time delay, instead of waiting 6 months to take a parallax measurement, you can pretty much do it at the same time. So that's kind of interesting. And Jennifer, you may have more to say about that.
No, I think that really is one of the unique things about New Horizons, right? To be able to get the simultaneous observations for parallax.
Yeah. So those are the few things that come to mind.
Thanks. Do all new commands get processed through the simulation New Horizons computer prior to uploading?
Yes, all new commands are first-time events. And then after that, we do reuse commands. We don't necessarily have to test them on the hardware simulator. We run everything through the software simulators. So yes, all new commands do get run through both simulators.
Yeah. Have the people on your mission operation team changed over the course of the mission?
You mean gotten older?
That's one part of it.
Yes, you know, as when you first start a mission, there's, you know, you have a large team because you're operating a spacecraft, the particular spacecraft for the first time. There are a lot of new things, and then as the mission goes on, you know, the teams get smaller, mostly because of funding gets, you know, more constrained, and you are repeating things. So people that might have started as flight controllers are now analysts. And we have a sort of a, we call it, it's a sort of an education program where you can shadow a different sort of discipline on the team and learn about that. So it is, yeah, in terms of that, so changed, yes, in terms of what people might be doing. And then of course, you know, it was launched in 2006, so.
A few retirements perhaps?
Yes, but you know, I don't think you ever really leave New Horizons. We have a lot of emeritus people on staff, and it's one of those missions, you know, if you say, hey, you want to be on a team that's going to Pluto, and you know, you pretty much got them.
For sure. How much of a trajectory change can you get out of the propellant that is left? Would you be able to maneuver to another object if you find one?
We have, so the amount of maneuvering we did to get to Arrokoth, we have almost as much left in the tank, maybe not quite as much. So about that distance. So it has to be within sort of the path of where the spacecraft is going. We can't do a right turn or, you know, probably even 60-degree turn. But we do have enough if we can find an object in the, you know, within that realm of the propellant. One of the things is that the Kuiper belt is theorized to go out to about 50 AU, and we're beyond that point. So the density of these objects is very, you know, small. And, you know, so our chances are decreasing as we move farther away from Earth.
And there's also challenges in finding it in the area that you're headed, right?
Yes, so less objects, and, you know, you have to be more constrained on where you can find them.
Yeah, and it's hard to find them with the background of the galaxy, right?
Yeah. Exactly. That's a very good point. We're heading towards the galactic center, which is very bright. So here we are, we're looking for very dark, small objects. So very good point. It's hard to pick those out of the background.
So related question about your occultations. How are those pictures generated by the occultation of the stars that creates the shape of the object?
How are the, so I'm not sure I'm following the question, but when the lines I showed of the telescope looking at the star, and then the breaks in them were breaks of the star. So you didn't see the star for that amount of seconds. And so it's, you know, they're, you know,
the Kuiper belt object passed in front of the star and blocked the light.
Yes.
Okay. And based on all your logging, we could infer the shape of it.
Exactly, because each one of those telescopes had a different amount of time where the star was not visible. And so that sort of made the shape, you know. So this one had a smaller period where the star blinked out. This one had a larger period and so forth. So sort of like that.
Very, very fascinating that we can do this, right?
This is amazing. It truly is amazing. Yeah.
So I think we have time for maybe one or two more questions. Here's one. How much drive space is on the various data storage areas, and how much time does it take to transfer and or download information?
That's a good question. So each recorder, we have two of them, a primary one that's tied with the primary side of the spacecraft, and a second recorder, which we call a redundant one, which wasn't really redundant when we flew by Pluto. Each of those recorders holds 64 gigabits of memory, which engineers thought, oh yeah, that's plenty of space, but no. There's always more science.
Isn't that always the case though? Like
it is.
It's like you buy your new smartphone and you're like, oh, 256 gigabytes should be more than enough. And you're like,
right. Exactly. And so for the flyby, we actually used both of those recorders, and the only data that was recorded redundantly on each recorder were the group 1 objectives, and then the rest of it was, unique stuff. So as we move further from Earth, our data rates decrease. So when we were just after Pluto, we could probably get about 4,000 bits per second with a 70-meter antenna, which I know you're smiling, it's very slow, but actually for us,
bits, or not even bytes, but bits, right?
Bits, yes. And now the max we're getting is about 1,000 bits per second. And that is with, we have enough power so that we can send 2 signals down from the spacecraft, essentially doubling the rate of downlink that we would get with just a single. So at some point, we're not going to have enough power to do that, and it will really get slow.
All right, one very last, hopefully quick question. What is the anticipated remaining lifespan of New Horizons?
So we predict, its power is the limitation. So we predict mid-2030s without any change to our baseline sort of power concept. But our mission system engineer, other people on the team are working really hard to try to figure out how we can make it last longer. I know that our mission system engineer has a goal of 2050. I'm not sure we're going to get there.
All right.
We're continuing to work on that one because we're such a unique spacecraft, just like the Voyagers. There's only a few of us out there.
Great. Well, thank you so much for taking the time to talk to us about the mission operations and answering our questions. Thanks to all of our viewers out there. And I hope we'll see you again soon. Thanks.
Yeah. Thanks so much for having me. Thank you.